I was struck by the fact that she said that there were, I think, 8 million metric tons of plastic going into the ocean every year.
It's kind of overwhelming.
I'm coming in knowing that there's an issue, but leaving like, oh my gosh, this is like bigger than I even expected, and I knew it was a big problem.
Good evening. Thank you very much for having me here, and thank you for the intro. Can everybody in the back hear me all right? Cool. All right, so I'm going to give you first a little bit of background about SEA, Sea Education Association, and then we'll go into the meat of the talk, talking about plastic, kind of starting more generally about plastic in our marine environment and the big picture of the problem and the state of the science. So what do we know and what do we not know? Talking a little bit about the issues, and then finishing with the solutions. So what can we do about this problem from a broad scale to an individual level? Feel free to stop me if you have a question. If you raise your hand, I'll try to notice and answer it. I don't mind stopping. And then we'll try to leave some time at the end, too, for some questions and discussion. So happy to do that. So some of you might be familiar with SEA. I've already talked to a few alums tonight, which is great. But for those of you that are not familiar, SEA is a nonprofit organization in Woods Hole, Massachusetts. So we're separate from Woods Hole Oceanographic. We've been around since 1971, and we primarily run a study abroad program called Sea Semester. So we take students out sailing, primarily undergraduate students. We do take some high school students in the summer out. And we take them on a ship that looks like that. We have 2 ships, one called the Robert C. Siemens that sails in the Pacific, and one called the Corwith Kramer that sails in the Atlantic. And the students learn about oceanography, environmental science, navigation, sailing, environmental history, and they become crew members on board. And so this is a pretty unique platform because we have a whole laboratory on board, just like the big research vessels, just kind of in a small form, and we're doing science under sail. So it's a little bit more dynamic, but it gives us a really unique opportunity because our ships are out there sailing year-round to the same places year after year and constantly sampling every single day. So it gives us the biggest data set of its kind of surface plastics collected at, in the Neuston layer at the surface of the ocean. So that's kind of a little bit of background about where our data set comes from that I'll be talking about, and I'll get a little bit more into how we actually collect those data as well. So plastic in the marine environment is kind of having a moment right now, I would say. You hear a lot about it in the news, which is great, because that means more and more people are learning about it, more people are aware of the problem, and that is more people to do something about the problem. And I was really excited to hear about the initiatives that are happening right here in Norwell and the local towns as well. So just some examples of places like CNN, BBC, New York Times, National Geographic. All the major news outlets are looking at this problem and starting to get it out there. About 10 years ago or more, when this issue started getting some publicity, this was the main story that was told. How many of you have heard of the Great Pacific Garbage Patch? Probably most people. That terminology is still used. It's not my favorite terminology because I think it leads to a little bit of a misconception of what the problem actually looks like. So often when you hear that term, you see a picture that might look something like this. It's quoted to be the size of Texas or twice the size of Texas. But when you're actually out there sailing in this region where the plastic does accumulate, you don't really see this. It doesn't look like that. It looks like this: sky, sea, wind, waves. You can't really see it from the deck of the ship very easily. There's the occasional boot or bucket or fishing gear like the previous picture showed that might float by, but that's not an everyday occurrence. The ship's not pushing through this pile of trash. What it really is just a high concentration of these tiny, tiny microplastics like that picture up there. And most of them are considered secondary microplastics. So these are things that started out as a larger item that we would recognize, and then the UV light from the sun makes plastic really brittle and wears it down. And then it's really easy to break. So as it's out there getting beaten up in the wind and the waves or the sand on the beaches, it breaks apart into these tiny particles. It makes it really hard to tell where it came from, to tell what it started out as. And we don't know a lot about the process. We don't really know how long it takes yet for these, that cup to turn into that handful of microplastics. But we do hypothesize that as the size gets smaller, the risk goes up. Because now you have more particles out there, and they're so small that they can be consumed by pretty much everything in the whole food web. So it's really, ubiquitous across the marine environment. And, not just at the sea surface that we'll be talking mostly about tonight, but also washing up on beaches, in our sediment cores and our ice cores. So, taking ice cores in the Arctic, they're finding little bits of plastic in these really remote places where, there's very little human impact, but we're still seeing the human impact at this tiny level. And it's not necessarily just the marine environment, it's also in freshwater systems like lakes and streams, even surface runoff, and then in things like our sea salt, bottled water, and some recent studies have even found particles that are so light they can be carried in the atmosphere. So really just across the entire globe, not just the marine environment, we're finding these little bits of plastic. So something that, large scale, we need to start thinking about. So this slide talks a little bit about plastic in general. So plastic is a pretty broad term that actually encompasses a lot of different compounds that are chemically different and have different physical characteristics. One of those physical characteristics that is different is the density. And that's something that can impact where the plastic ends up when it enters the ocean. So if something is denser than seawater, it's going to sink down and end up littering the seafloor. The things that are buoyant will end up floating out into the gyres and collecting at the surface. And so some of the common plastics that we use every day fall into both of those categories. So here you see the recycling codes that you probably recognize, numbers 1 through 7. The common ones that we find floating out in the gyre are numbers 2, 4, and 5. Those are polyethylene and polypropylene. Those are things like milk jugs, plastic bags, bottle caps, straws, all those common items. It's a pretty bendable plastic. Number 1 is also a very common plastic. That's PET. That makes up our water bottles and our soda bottles. And that plastic is actually denser than seawater. So once you take the cap off the bottle or the bottle breaks open, it will actually sink down to the seafloor. PVC, kind of plumbing pipe, that sinks down to the seafloor. Polystyrene is a little bit tricky because it has 2 forms. It can either be a solid form, which is a pretty brittle plastic that you might find like a takeout container made of sometimes, and that actually sinks. But the common form you find polystyrene in is styrofoam, so foamed polystyrene, also takeout containers and cups, and that obviously floats because it's very buoyant. And number 7 is a catch-all category for every other type of plastic. So it's kind of hard to pin that down. Most of those plastics sink, though, things like nylon, PLA, a lot of other textile-type fabrics. Those are all mostly denser than seawater. And so that kind of gives you a picture of where things might end up if they were to enter the marine environment. So what happens when it enters the marine environment? I'm sure you've probably seen pictures like this and heard stories about the impacts, but I just wanted to touch on them briefly. Larger debris, things that aren't broken down yet, especially fishing gear or packing straps, those 6-pack rings, things that are kind of linear or circular, those can be big entanglement risks. So animals can get caught in them, especially when they're little and maybe not grow properly, like that turtle on the bottom there. Or if a marine mammal were to get stuck in them, they might not be able to resurface and catch a breath, like a whale or a seal, something of that nature. And they also act as a new substrate. So this is kind of a lesser talked about problem, but that it's something that's out there that wasn't out there 100 years ago. And communities of organisms tend to accumulate and grow on the plastic itself or underneath the plastic. So things like barnacles, there's a crab on this ball here. And then these pieces of plastic are transported across ocean basins to places where these organisms are not native. So it could be a kind of a way to take an invasive species to a place it doesn't belong. An example of that is the tsunami in Japan. About 4 or 5 years later, all the debris from the tsunami was washing up on the coast of California, Oregon, and with it were coming species of organisms that they'd never seen in those parts of the world before. So to my knowledge, there hasn't been any, no organisms have taken hold yet from this, but it's definitely a way that could happen. And it's not just at the large scale. even at the microbiome level, when you start looking under a microscope and looking at the microbes that are living on these plastics, the community is very different than the community in the surrounding seawater or other natural substrates. So even looking down at that level, we're kind of changing the ecosystem and what's out there and how it's interacting. The other one, that's probably the most commonly talked about issue, is that everything eats it. So everything from the tiny zooplankton to fish, birds, sea lions, turtles, it's pretty much across the food web, things have been found to consume plastic accidentally. That can have a whole host of problems. This seabird here ate a lot of larger items like bottle caps, lighters, things that it couldn't pass through its digestive system. And so then they end up starving because their stomach is full, but they're not getting any nutrition. And so that's just one example. That doesn't happen in every case. You know, there's some species that might just pass the plastic right through their system. If they're eating, you know, jagged or irregular pieces, it could damage their digestive system. But, you know, it's probably not good to be consuming a lot of plastic. And one of the big questions that comes along with this is, what about the chemicals that are with this plastic? And that's a pretty difficult web to untangle, and there's a lot of scientists that are actively studying this question. And usually in a laboratory study, you'd study, you know, maybe a specific species or two and a specific chemical at different levels. But out there in the marine environment, there's a whole host of chemicals at all different levels and all different interactions. So it's going to take a long time to really get to those answers. But plastics, when they go into the ocean, they're not just the pure plastic itself. They often have a lot of additives, things like plasticizers or phthalates, BPA, dyes, some things that can act as like an endocrine disruptor that might mimic a hormone in your system. And then they also pick up chemicals along the way. So they kind of act like little sponges, picking up chemicals that are just out there, legacy contaminants that are floating out there. And so how they interact with the animals depends on, you know, what the animal's already been exposed to, how much plastic they're interacting with, how much they're interacting with chemicals just that have nothing to do with plastic, just passing over their gills and things of that nature. So it's a lot of questions there, but it's, you know, probably not positive, adding all these kind of unknowns into an ecosystem like that. And in general, kind of what we know about the impacts of plastic on the marine environment, we don't have answers in terms of the ecosystem level yet. So when you're thinking large scale, how is this impacting an entire species or an entire ecosystem, we don't have those answers yet. We know how it's impacting, you know, an individual if you find an animal that's entangled or has eaten a lot of plastic, but taking that up to a large scale is still in the works. All right, so now to talk about how do we study this problem? How do we go out and actually study what's out there and figure out how much plastic there is, where is it accumulating, how is it changing over time? And so the way we do that is on our two ships. The one pictured here is the Robert C. Siemens, SEA's Pacific vessel. The Corwith Kramer is our Atlantic vessel. And so our students come and they usually stay in Woods Hole for about 6 weeks, studying oceanography, studying maritime history, learning nautical science. And then they go out to sea for 6 weeks and study those things firsthand, learning how to deploy all the oceanographic gear, collect their own data, design their own research projects. And we get students from all over the country and all over the world, all different majors that come and sail with us. Kind of a common theme running through most of our programs is environmental awareness and thinking about environmental problems of our time. So things like climate change, sustainability, biodiversity, environmental justice. We have some programs looking at coral reef health and doing coral reef surveys. And of course, plastics is kind of a common thread running through almost all of our programs, that students are out there actively sampling the plastic in the environment and studying it. And our kind of tagline is creating ocean scholars, stewards, and leaders. So our hope is that the students leave the program with a greater understanding of the ocean and a greater awareness of what they can do to help the ocean and the environment. And these are our cruise tracks. So the good thing about these cruise tracks is they are pretty consistent. So year after year, we're going to the same places, sampling the same waters about the same time of year. So here in the North Atlantic, we're up in New England in the summer, typically from Woods Hole to Maine, sometimes Canada. and then we head south to the Caribbean for the winter. And that kind of north-south transit, we usually go out towards Bermuda, and we hit an area where there's a lot of plastic on that transit. We've been doing that transit for decades and collecting plastic data since the early 1980s. So we have over 30 years worth of data in that same part of the ocean, sampling every single year. So that's the largest data set of its kind in the entire world, and it's a pretty unique resource just because our students are constantly out there doing this work and studying what's out there. Our Pacific ship is in New Zealand right now, and then they'll head up to Tahiti, to Hawaii, down to Fiji, Tonga, some really rough places to go sailing. We used to spend more time going to California and kind of going through that Great Pacific Garbage Patch region. We've, about 4 or 5 years ago, changed our cruise tracks, so now we're going down to New Zealand. Turns out people really like New Zealand. But we're getting a little bit of data in the South Pacific now where there's not very much information, so that's pretty interesting. All right, so how do we actually collect the plastic? We've been doing the same method since the 1970s. So we have this net pictured here called a Newston net. It's towed right at the surface of the ocean, so the net's actually half in, half out of the water. It's just sampling the upper 25 centimeters or so. It's a meter wide, and we tow it at a slow speed going 2 knots for about 1 nautical mile or 1.8 kilometers. And so we try to tow it twice a day, every single day. So at noon and midnight, we get a daytime and a nighttime sample, and we tow it about the same distance. We use a GPS to make sure we know exactly how far we towed it, and then we can figure out how much water passed through the net. It's typically about 2,000 bathtubs worth of water that we're sampling in each of these net tows. And once the net comes out of the water, we dump the contents of the jar through a sieve, and then students visually pick out every piece of plastic and quantify it. They're not just studying plastic, they're also studying the diversity of the organisms that they're finding in there, the quantity, all kinds of other questions as well. But plastics is one of the things that we collect that way. And the mesh of this net is 1/3 of a millimeter. Yeah?
And what do you do with it after you study it?
Good question. What do we do with it? With the plastic itself? We actually save it and we archive it at SEA. So that was my first task when I started here about 5 years ago, was to inventory 30 years worth of data in the basement. It took a lot longer than I thought it would, but got through it, and we save it, and we do other research on it as well. So I have a few slides talking a little bit about what those samples do once they're back on shore. All right. So that mesh of the net is 1/3 of a millimeter, so it's pretty fine mesh. Most microplastics are defined as less than 5 millimeters, so something like a grain of rice or smaller. But they get even smaller than that. They get even smaller to the point where they're passing through this net that we're using. So we're sampling a specific size range. And once you get smaller than that, it becomes really hard to study microplastics. There's not a ton of technology that's really keeping up with the need to sample that small. But this is an example of what the pieces we look like, what we find out there, what they look like. And then a reminder of what polymers are the ones we're commonly finding in our net. And so how we know that is we have this instrument called a Raman spectrometer, and it's an instrument that shoots a laser at the piece of plastic. You have to put everyone underneath it. It doesn't destroy it or anything, but it gives you this kind of spectrum here, which is basically a chemical fingerprint of what type of plastic you're looking at. So it doesn't tell you that it was a cup or a bottle or a bottle cap or anything like that, but it can at least tell you, narrow it down a little bit and tell you what type of plastic, which of those recycling code bins does it fall into. And what are the most common polymers out there? Are we finding the amounts we might expect to find? Are they behaving differently? And so beginning to look at some of those questions. And so that's one of the things we do with the samples when they come back, is we run a bunch of them underneath this instrument to try to get data like that. So over 5,000 pieces now we've run in this Raman spectrometer to really get a picture of what types of polymers we're finding out there in the ocean, at least at the surface. We also can use a scanning method to look at sizes. We can look at forms. So are we finding a lot of things that are film that might come up from a wrapper or a plastic bag? Are we finding a lot of foam or pieces of line that might come from a rope or a marine source? And kind of mapping that out and seeing where are we finding differences. When you look really close to the shore, are you finding something different than way out in the middle of the ocean? Do these change over time, decade after decade? And kind of beginning to look at some questions like that. One other thing that we can do with the samples is put them under a microscope and look at how they're actually physically degrading under a microscope. So those upper 4 images there are polyethylene, so that's like your milk jugs, plastic bags. And then the ones down here are polypropylene, also a common plastic, a lot of dairy containers, things like that. And if you kind of look at them closely, you'll notice the 4 down here look a lot brittler, they look drier, they're kind of crumbly. And the 4 up there almost look like waxy and sticky. And so it turns out that the two most common polymers that float at the surface of the ocean, you can actually almost visually identify them pretty well under a microscope. And that's not something we anticipated finding, but it just shows that not every plastic is created the same way, and they're all behaving slightly differently in the marine environment. So that's another question that people are starting to think more about, is not just thinking of plastic as a general term, but thinking of each individual type of plastic and how might it be behaving or impacting the environment around it. All right, so now for the maps. So this image here shows where we've collected plastic and how much we've collected. So if you look, each dot on there is a place we put that net in the water, and we sampled how much plastic is out there. The color of the dot indicates how much plastic we found. So the warmer colors, the reds, the yellows, the oranges, those are really high concentrations. The blues, low concentrations, and the dark blues are actually no plastic. So you can see it's not evenly distributed. This kind of zigzag pattern that you see in the middle there, that's a dedicated trip leaving from Bermuda to study plastics in the North Atlantic. And so their kind of goal was to get to the other side of that accumulation zone. They didn't get there because the furthest that they got out with the time they were allotted, they found that green star, which was the highest amount we've ever collected, 26 million pieces in a square kilometer. I mean, there's some pictures of this. You see like a bucket and someone dips their hand in, and it just comes out covered in all of these little bits of plastic. But you can start to see a pattern forming here that the plastic is accumulating in this middle region, and that's where the Great Pacific Garbage Patch comes in. It's not just in the Pacific Ocean. There's actually 5 of these places where plastic accumulates on the globe. And so this is a computer model where they look at surface currents and where water would bring things if something was floating in the ocean. And you can see that there's a North Atlantic, a South Atlantic, North Pacific, South Pacific, and an Indian Ocean accumulation zone. So these are called subtropical gyres, and it's based on the ocean currents. You've probably heard of the Gulf Stream, a really fast current that runs up the east coast of the US, and then it kind of turns out, and there's fast currents running along the equator, kind of in the other direction, kind of creating this almost vortex of flow where things are pushed into the middle, and then that's a really low flow region inside the gyre. So once things are pushed in there, there isn't really a way out except to sink. And so these plastics are buoyant, so they're not going to sink out. So things are being pushed in, and that's kind of the end of the line where they're just going to accumulate. And so that's where you get these accumulation zones of plastic. Here's our data from the North Pacific. So this is kind of that garbage patch region. And one thing to note here is when you look at the equator, that 0 degrees right there, it's actually pretty rare to find a piece of plastic near the equator. Those are mostly dark blue dots where there's 0 or 1 pieces found. And that's because the equator is a divergent zone. So you have that trade winds blowing along the equator and kind of going off this way and taking things away from the equator into those accumulation zones. So it's not a place you're going to find a lot of plastic. So you can see that it's not evenly distributed in any way, but you see that really highly concentrated area where that box is drawn. So we can then spatially average all these dots together to get a bigger picture of where we're finding this. And this is where we can compare it to computer models. So you see the gray line and the black line and the dotted line. Those are all different computer models that predict where plastic would end up. And we can use our data to actually ground truth those models and make them better and see, are they actually accurately predicting what we are actually finding. That's one positive there, I guess. You can use it to make the models better. And then we can also use it to figure out how much plastic is out there floating in the ocean. So about 21,000 metric tons is the estimate from this data set floating in the Pacific Ocean. And then another scientist, Eric von Seibel, has taken our data set along with every other data set in the world that we can find that has information about surface floating plastic. So if you kind of look at that map there on the left, you can see the SEA data sets that I just showed you. They're actually the most covered regions are those regions where we've collected data. And then there's other groups that have collected data in some other parts of the world. And you can take that and make a whole global estimate of how much plastic is floating at the surface of the ocean. And the estimate is in the 100 to 200,000 metric tons. So just remember that number, because we'll come back to it in a minute, of a comparison of how much is going into the oceans. So it's a pretty big number. All right, so now if we kind of switch to not just studying what's out there in the ocean, but what's going into the ocean. So what do we know about where does it come from, how does it get there, and can we estimate how much is actually going into the oceans? And so where does it come from is a good question. The middle picture here is a picture of the LA River, and that's after just one rainstorm. So this is all of the waste that was sitting somewhere to be washed into the LA River, so on sidewalks or streams. And just one rainstorm washed it all into the river. At the top of that image there, you see a boom, and they actually have that there to stop the plastic from getting all the way out to the ocean. So that's a good thing, that all of that didn't get out to the ocean. But you can imagine if it didn't, that would just be one day's worth of trash getting into the Pacific Ocean. So a lot of it can come from just mismanaged waste. Anything that doesn't end up in a secure container being taken to a secure place where it's not going to be blown away by the wind. So like that overflowing trash can there, you can imagine if it got windy or if it rained, all of that stuff will be washed down a storm drain or down eventually into a stream, which could eventually make its way out into the ocean. So some of it might be intentional littering, but some of it might be people trying to do the right thing and just not the resources to really keep up with how much waste we're producing. Another source is fishing gear. So this image here is a whole bunch of fishing nets sitting on a remote island. So kind of a more at-sea source. And it's actually illegal internationally since the 1980s, I think late 1980s, to dump plastic in the oceans from a ship. So there's this MARPOL regulation. It doesn't mean that everyone follows it or mistakes aren't made, but it is internationally illegal to dump plastic in the oceans. Another source, kind of on the smaller scale, is what comes out of our wastewater already. So things that are already so small that they're in our wastewater stream. And that might be fibers. Fibers are getting a lot of news attention right now. It might come from clothing or furniture, things that are so small that they're making their way right through the wastewater treatment plants and getting right out into the water. A lot of our clothing is made of synthetic materials. A lot of our furniture is made of synthetic materials. Another one are microbeads, and so they're actually banned in the US now, which is great. It was a bipartisan law that banned microbeads in face washes, but some other places still use them. But basically they're tiny beads that you scrub your face with and then wash them down the drain. And then they're also so small that they don't get removed very well in a wastewater treatment plant. So using the data about mismanaged waste, one of my colleagues, Carol Lavender-Law and Jenna Jambek and a few others created the first estimate of how much plastic is going into the world's oceans. So they looked at how much plastic is produced, how much is used, how much is mismanaged, how does each coastal country manage their waste, and used that to narrow it down to an estimate. And the mid-range of that estimate is 8 million metric tons. And so this is data from 2010, so it's probably a little bit higher now. But 8 million metric tons is equivalent to if you took a grocery bag full of recyclables and you stacked up 5 of those, so about as tall as I am, and you put that stack on every foot of every coastline around the entire planet, that's 8 million metric tons of plastic. So a pretty staggering amount, and that's just 1 year's amount of plastic going in. So that's cumulative year after year. It's more than the amount of tuna that's being taken out of the ocean, so we're kind of trading fish for plastic. It's not really a fair trade for the ocean. And they also looked at it by country, so which places have the highest input of plastic. A lot of that comes down to how many people live in each country, how many people live near the coast, and how much plastic is used by each person. So the US and the European Union ranked in the top 20, and that's not because our waste management is bad, but it's because we use so much plastic per person. So even though we have a very small percentage of it that gets lost into the ocean, there's just so much of it for every person that lives near the coast that it still puts us up there in the top 20. A lot of other places that ended up in the top 10 or top 20 are places that don't readily have waste management infrastructure to keep up with the waste stream that they're dealing with. And here's just kind of a representation showing that that 2010 value is likely to keep increasing because our production of plastic is continuing to increase. It's not really going down anytime soon. All right, so I kind of threw out a whole bunch of numbers there, but if you look at them next to one another, so 8 million metric tons is the amount that's going in 1 year, and then 100 to 200,000 metric tons is the amount we're finding floating at the ocean, floating at the surface of the ocean. So you would expect that things aren't going away, plastic isn't biodegrading every year, so those numbers shouldn't even equal each other. You should find a lot more than we're finding. So it turns out that there's kind of this huge piece of missing plastic. So about less than 10%, depends on which numbers you use, but a very small percentage of what we would expect to find we're actually finding at the surface of the ocean. So that just shows that there's so many unanswered questions that until we fully understand how this plastic is behaving and where it's accumulating, we're not really going to be able to understand all of the impacts on the ecosystems or what we can even do about this problem. So we're just looking at one reservoir here, the sea surface, but the ocean is much bigger than just the sea surface. So there's a lot of unanswered questions here. So how much is on beaches worldwide? We don't really know yet. How much is in sea ice or on the seafloor? Also not really known. We know that there's stuff on the seafloor. We've seen pictures of it, and we've found it in sediment cores. But the seafloor is a very difficult place to get to and to study. It's very expensive and it's massive. So we don't really have a large-scale estimate of how much is out there on the seafloor. We also don't know how much is actively inside fish or turtles or birds and swimming and flying around. So that's another place that we don't have an estimate. And we don't know how much of the really tiny stuff there is. I talked about that timeline of how long it takes a cup to turn into microplastics and what happens next. So when you start looking really, really small on this scale, there's even more unanswered questions. So it just kind of shows that this area of research is a relatively new area of research in terms of the scientific community. And so there's still a lot of basic things that we don't understand yet. One other important thing here is the water column. So the average depth of the ocean is about 4,000 meters, and we're just sampling 25 centimeters. We also take into account wind mixing, so really thinking down to maybe 20 meters or so. So we've done some experiments taking these particles that we've collected and putting them in this column and watching them float to the surface. It's very tedious, but it kind of gives us some numbers of how quickly will these particles float back up if they're mixed down because of a wave or the wind. And so that's all thought about in these models, and that doesn't really help find the missing plastic. But below that 20 meters down to 4,000 meters, that water column is also a place that's really hard to sample, really hard to get to, difficult to, expensive and difficult to get to. So another place that we just kind of don't know how much is out there yet. And here's just a picture of what's on the seafloor in one place. This is over in Newport, Rhode Island. A group called the Rosalia Project captured this image. They call it Beer Can Reef. It's just this huge pile of junk sitting on the seafloor in the harbor right there. All right, so now we've talked about the problem, kind of the large scale, where is the plastic, what form does it take, what does it do to the environment, what can we do about this problem? So this is kind of just a brainstorm of solutions. And so since it's such a complex problem, there's not one magic solution that's going to fix the whole thing. It's going to have to come from a lot of different angles and a lot of different people. So kind of just walk you through my messy diagram here. One of the things is limiting the source. So limiting how much plastic gets into the ocean. So that might look like improving waste management infrastructure, especially places that don't really have the infrastructure to keep up with the waste stream. That could be a really big source of helping stop it from getting into the ocean in the first place. Another kind of limiting the source thing are beach cleanups. So things that are sitting on a beach are usually pretty large. They're pretty easy to collect. And you can get them before they're washed out into the middle of the ocean where it's much harder to get to them. Another thing is innovation. So there's this, you may have heard of Mr. Trash Wheel. It's this thing in the Baltimore Harbor. It's a big solar and water powered wheel that they use to scoop up all of the trash floating down the Baltimore River and put it into a dumpster so it doesn't get out into the ocean. So that's a pretty unique, innovative resource that's really stopping stuff before it's getting out into the ocean. Because once stuff is out there in the middle of the ocean, it's really hard to collect and to get to. You've probably heard of the Ocean Cleanup Project. It's been a lot in the news about that lately, trying to put this big boom out into the middle of the Pacific Ocean to collect the plastic. I think that is, they have a lot of enthusiasm and some good ideas, but it's, not the magic solution that people want it to be. Because even if we stopped picked up everything in the middle of the ocean right now, if we didn't stop putting it in, it'd be back there in, a few months. So it's really not going to solve the problem like we hope it would. And also, there are some concerns about all of the biological stuff that's out there and, potentially impacting some of the things that are out there as well. Another thing that needs to be done is just reducing the amount of plastic we use in general. So plastic is a pretty useful resource. It's something that you need in the medical field, you need in the scientific field, you need for all kinds of things. And it's meant to last a really long time. So it's very useful. But a lot of the things we use it for are things that are not meant to last for a very long time. So that's one of the places where we can make some changes and reduce the amount that we're using. And that might come also in the form of innovation, maybe different materials, different products. It might come in the form of policy changes like bag bans or styrofoam bans. Extended producer responsibility, so making producers more responsible when they produce a product for thinking about the whole life cycle of that product, not just producing it and getting it out there, but having a plan for how it will be recovered and reused or recycled. Also, just at the individual level, more awareness leads to more behavior change, and the more behavior change there is, the bigger an impact that can have. And kind of on that note, I like to show this image. This is from the Ocean Conservancy, the International Coastal Cleanup. So every fall, there's this big coastal cleanup around the entire globe. Everyone tallies up how much trash they find in their town, what type of trash it is, and then they send that data to the Ocean Conservancy and they compile it all. And so I think this one's from 2016, but each year the top 10 items is pretty similar. And so if you look at these kind of 10 most collected items on a beach, you'll notice a common theme that almost every single one of them is a single-use item, something that you use one time and then you discard, whether it's recycling or throwing it away. So cigarette butts being number one, but most of the other ones are related to food and beverages, water bottles, straws, stirrers, lids, caps, containers, wrappers, bags. And most of those things all have available alternatives. So whether it's a reusable water bottle, a reusable coffee mug, reusable bag, a reusable straw. Wrappers are a little bit harder because you can't really control how something is wrapped at the supermarket, but you can choose options that have a little bit less packaging. So instead of really individually wrapped things that are wrapped multiple times, picking something that's more bulk wrapped, usually has less plastic per item that you're buying. But just something to think about, since the stuff we're collecting out in the ocean, we can't really tell what it started out as or where it came from. But when we collect stuff on the beach, it kind of gives us a picture of what the stuff in the middle of the ocean might have been, because this is the most common stuff that we're collecting on our beaches. And so since the most common stuff are single-use items, that's actually some of the easiest stuff to change our behavior around as well. So one of the things that we've been doing down in Falmouth and Woods Hole is creating this group called Trash Shouldn't Splash. And so it's a collaborative effort through SEA, NOAA Marine Debris Program, and the Falmouth Water Stewards, which are a local nonprofit. And the Falmouth Water Stewards, there's a group of girls called Skip the Straw. And so they started this movement when they were in 5th grade, and now they're in, I believe, 7th or 8th grade, where they've been talking to businesses, they've been talking to their schools about reducing straw use. So it's kind of something that not everyone will need in their drink, but is often automatically put in their drink whether they want it or not. So trying to kind of change small behaviors like that in restaurants where straws are available if someone needs it, but not just automatically put in every single drink that goes out. And we've kind of expanded on that to not just straws, but all single-use plastics in the businesses in town. So we've partnered with the restaurants in Woods Hole, and we've had a really positive outcome. Everyone's been on board. I mean, and I know Woods Hole is a pretty unique place to do this. It's a very environmentally minded community. But we're creating a toolkit that could then be taken to any community that people wanted to implement this, whether it's talking to their local businesses, talking to their schools, and reducing plastic in all of those places. One of the things we did is involved local schools by doing an art contest. So these are pictures by K through 12 students that we then used to make flyers and display items that we gave to the businesses so that they could display them in their businesses. So kind of a good way to involve the community at different levels, from schools to business owners, and trying to do it all in a business-friendly way. So we don't want businesses to lose money or lose business by doing this, but trying to work with them on solutions that can actually help their business. One of the things we did is we had some C semester students go out and interview, taking a survey, interview people that are in town, people that are at these businesses that are wandering around Woods Hole, and kind of get their opinions about it. So do the patrons that are going to these businesses want to see less single-use plastic, or is that something they don't really care about? And it turned out that a huge percentage, it was 90-some-odd%, wanted businesses to reduce their plastic use and didn't necessarily want the straw in their drink and those kinds of things. So then you can go and show the data and say that, you know, people aren't necessarily going to be opposed to this, they're probably going to be on board. And so just a few more examples of some of we got some really great artwork. We got some cool recycled water bottle chandeliers that are hanging at SEA. So some really neat stuff that came out of this. And then getting more students involved, talking to their peers. And the Skip the Straw girls have done presentations at their schools and talked to the other students as well. So it's a really, really great thing, getting things moving along. This has a website called trashshouldn'tsplash.org. You can check it out pretty soon. Probably in the coming weeks, we'll have that whole toolkit available. So if anyone wanted to take any bit of it, whether it's the art contest or the talking to businesses or the survey and many other things, and implement it in their community, people are welcome to do that. All right, that's what I got for you. Any questions? Yeah.
Were you guys testing fish too?
Yeah, the question was about testing fish. Personally at SEA, we're not, just because that's a hard thing to test out when we're out there, you know, sampling. Fish are take a lot more time to actually catch them and do it scientifically. So we personally haven't been doing that, but I know there are some researchers. Chelsea Rockman comes to mind as someone that studied fish that are available in commercial markets and looking at, you know, what you might be finding in those species. So it's definitely something that people are looking at in the field.
Yeah. Are we at a point where baleen whales or similar kind of filter feeders is there any measured effect yet that anybody's studied?
Oh, that's a good question. Not that I'm aware of. I don't want to say no definitively, but you know, whales are another thing that are pretty hard to study, just hard to interact with in a way that's not harmful, and hard to interact with enough of them to have a meaningful data set. So I don't know of any large-scale studies looking at baleen whales, but I know there's been, you know, anecdotal evidence of whales washing up that have have plastic in their stomach and things of that nature, but not anything robust that I'm aware of.
Yeah.
Are you aware of any data about damage to human health? Because that was a question that came up over and over and over again in plastic bag ban struggles. Does it actually hurt you?
Yeah, that's a very good question, and that's, I think, one that is difficult to answer, and especially when we're thinking about, you know, fish in the marine environment. If you're thinking about kind of how much plastic we're exposed to, the fish we're eating is probably a very small piece of that. We've done some things with our students to have them think about how much plastic they interact with every day, so to keep like a notebook and think about every plastic item that you interact with. And it's kind of overwhelming when you do that. If you kind of think through your day of how many things are plastic that we touch or that we eat out of or that we wear, you know, it's a huge amount. So how that's impacting human health, I don't have an answer, but you know, there's a lot of chemicals that go along with plastic production and additives to the plastic. Some of them, you know, BPA comes to mind. That's a known endocrine disruptor that kind of mimics hormones and might mess with the endocrine system. But how that's kind of large scale impacting us, I don't know. It's probably kind of in a big experiment. It's a very good question though.
Yeah.
I worked for Woods Hole Oceanographic for 10 years. I was in the engine room, so I don't know much about science. we did a lot of, we had modules that we drop over the side. They might have 12, 24, 36 plastic containers with the tops and bottoms. Bring them down to a certain depth, bring them up, and close them at various depths. And then the science would get them all, we would take samples and test them. And I was talking to one of the scientists one day, and he said that no matter where they take the samples, in any part of the world, they always get traces of freon. He said freon is a man-made item. And I just thought that was fascinating.
Yeah, that is very fascinating. We do a similar thing at SCA. We have a CTD rosette or carousel. So it's an instrument that goes down and it measures the conductivity and the temperature as you go down with depth. And then it also has these bottles that you were talking about called Niskin bottles that kind of take a snapshot of the water, close at different depths, and then you bring it up. And so we can use that for all kinds of chemical analysis, whether it's looking at nutrients. But we've recently been starting to filter some of those samples onto filters and look at the really small stuff. Kind of dye the sample so the biological material would be dyed, and then the plastic wouldn't be dyed, and looking at what we're finding. So it's something that, starting to look at that water column. But that's really interesting that they found freon everywhere. I had never heard that. But we have been finding little fibers and little bits of plastic in some of those bottles as well.
Yeah. Do you measure like any gas or particles that come off the plastics and poisons? I'm sure that you have some sort of data.
Yeah, that's a good question. Gases. So it's not something we've been working on at SCA. We don't really have the laboratory on a ship our size to do something like that. But I know there's been some people, I think at Northeastern, that have looked at even like the carbon cycle in terms of plastic. So greenhouse gases and how are these particles behaving? What gases are they emitting? So I think the science is kind of going in that direction to look at that a little bit more in terms of maybe doing a controlled laboratory experiment, and it's a very good question.
One of the biggest problems with the ocean is the rise in sea temperature. Do you have any studies of, say, what the impact of plastic, being that it could exacerbate the temperature around the salt water or not? I would think that it would have some type of effect. Yeah,
that it's something I've thought about, but I don't know of any studies. Doesn't mean they're not out there, but not that I've personally read. But yeah, if it is at the surface, it could be impacting how light interacts at the surface. And also in terms of, kind of multiple stressors. When you're thinking about an ecosystem, if they're already dealing with an increasing temperature, and then they're also dealing with, plastic contamination.
That increases its density, it increases the absorption of heat from the sun. And I'm assuming, just assuming that plastic would aid that density. And so I just was curious if there was anything formally done.
Yeah, that's a really good question. Not formally that I know of, but definitely something interesting to think about.
Where does SCA get funding?
SCA gets its funding from a variety of sources. A lot of it is tuition-based funding and donor-based funding from our alumni and friends. So it's kind of broad scale. In terms of the research side, we've had some grants like an NSF or a NOAA grant to do some of the laboratory work we've done on plastics. So it kind of comes from all sources, but the organization as a whole is mainly tuition and donation-based.
What do they do about recycling? Is that industry involved so that they can separate out the different components and reutilize them?
It is evolving, I think. I think it's in the process of continuing to evolve. And recycling is one of those things that's very location specific. So, how you recycle here might not be the same way that we can recycle in Falmouth or in Rhode Island. It kind of depends on where your stuff goes and what system they have there. I think I read online that the next talk is about recycling, so hopefully next time you guys I would be interested to hear that and learn about the systems here.
Yeah.
What is the raw material that makes plastic?
It's all petroleum based, so it comes from oil, really. Some of it can be made from corn or from biosources, but the primary thing is oil.
Is some plastic better than other plastic?
Oh, good question. It depends on what you're thinking about. In some ways, there's some bioplastics, and bioplastic can be a little bit of a wishy-washy term that can mean a lot of things. So a bioplastic might be something that's made from a bio source, so a corn or a plant material, but in the end, it's the exact same polymers, the exact same type of plastic. So when you're thinking about waste streams and about stuff ending up in the ocean, it doesn't really matter which one you have, but if you're thinking about kind of greenhouse gases and where it comes from, then it does make a difference. There's also some plastics that are compostable or biodegradable, like PLA, polylactic acid is one of those. But that is compostable only in an industrial composting facility. So it needs to be at a very high temperature in a really specific environment. So if it ends up, in the natural environment, it's not going to biodegrade because it's not hot enough. And so those, if you live somewhere that has an industrial composting facility, can be a good alternative, but most places don't have that. So then they just end up in a landfill as well. So kind of something that our whole waste stream and management needs to keep up with those types of materials.
Are the plant-based materials being developed that can replace plastic?
Are they being
Rather
what?
than plastic bags, but put off bottles and other materials that don't need plastic. This is something that can be biodegradable.
The bio-based ones? Some of them. So it kind of depends. They can take the carbon from a plant material and turn it into PET, which is the same PET that would be made from petroleum. So then it would behave the same way. But they could also turn it into PLA, like I just mentioned. And so that would be compostable, but only at a really high temperature. So in the ocean, it would sink. They're pretty dense, so they would sink down to the seafloor where it's usually pretty cold and there's not a lot of light. So it would still persist like a petroleum-based plastic as well. And yeah, so it really depends on where they end up.
If you're out to restaurants or takeout food and you see plastic forks and knives that say compostable on them, it's pretty much a waste of time and effort in a sense.
Kind of, yeah. I mean, it depends where you are. There are some cities that have industrial composting pickup. I know in Woods Hole, there's actually a private company that has a composting setup that can compost that kind of thing, and most of the businesses have pickup by that company. But it's not a solution, especially if on a large scale, if that's the majority of a composting pile. I'm not sure if it would really be as conducive as a lot of plant material with a little bit of that compostable plastic. So yeah, we can't just switch all single-use stuff to a compostable option. But in some cases, it can be helpful as part of the solution. Yeah. All right, thank you.
I thought it was a fantastic lecture tonight, and the speaker had wonderful information, a lot of research to back up what she was saying.
I thought it was really informative. I thought Jessica was really knowledgeable.
I think it went well. It was nice to see such a big turnout. Lots of good questions, lots of interaction, and people really thinking about solutions and thinking about the issue. So it's always nice to have an interactive audience like that.